So can everybody see my molecule that's drawn in black font? It says functional groups by it.
Yes.
Okay, great. Well, let's see if we can identify some functional groups in this molecule. I noticed that I'm missing a hydrogen here, so I'll draw that in. I'll just throw this out there to my students. Does anybody recognize any of the functional groups in this molecule that I have drawn in black here?
Alcohol, maybe?
There's no alcohol in this one, so it might be a knee-jerk reaction to say, well, I know that if I have an R group, I know that if I have an OH like this, we call it a hydroxyl, you might think, okay, well, that's an alcohol, and I have one here, and I have one here. But something you want to do when you're identifying functional groups is you want to take what I call the 30,000-foot view. You want to look at the entire area surrounding the functional group. So this hydroxyl is attached to something else. Does anybody have another guess or another suggestion?
Alkene.
Carboxylic acid?
Oh,
A carboxylic acid. Yeah, absolutely. So if we have an R group with a carbon attached to it, and if it has a carbonyl and then a hydroxyl like this, this is a carboxylic acid. So I have a carboxylic acid right here, and I have another carboxylic acid right here. So these are both, this is a carboxylic acid, and I have another one over here. All right. Any other suggestions of any other functional groups in this molecule?
Is there R9?
An amine, yeah, there's two amines. There's two amines in here, absolutely. So if we have an R group and we have a nitrogen attached directly to it like this, and if that nitrogen has two hydrogens attached, we call that an amine, okay? If you have a nitrogen that has two R groups attached to it and only one hydrogen, it's still considered an amine. And if you have three R groups all attached to a nitrogen, it's still considered an amine. These are all amines. The difference between these three is that this one is called a primary amine, this one is a secondary amine, and this one is a tertiary amine. So it's based off of the number of R groups attached to the nitrogen. So right here we have a primary amine, right? This is a primary amine because the nitrogen has two hydrogens attached to it. What about this one right here? Can anybody tell me what kind of amine this would be? Based off of what I have in the
secondary.
Yeah, absolutely. So this is a secondary amine. Yeah, that's right. I'll throw another one out there. Can anybody recognize this functional group out here? Or just recognize this group?
The aromatic.
Aromatic, yeah. So if I have a ring like this, a six-membered ring, and the double bonds alternate like this is aromatic. So that's an aromatic. So we have an aromatic ring here. There's one more that might be a little bit tricky, and it's this one here. We have a carbon with a double bond to an oxygen, and then there's a nitrogen attached to it. When we have that, if we have a carbon with a double bond to oxygen and then a nitrogen attached to it, that's called an amide. So this is an amide. But if your nitrogen is attached to two hydrogens, like the one that I have drawn right here, then that is an amide. Oops, where's my pen? This is an amide. If your R group, then you have your carbon doubly bound to oxygen, and then you have a hydrogen and one R group like this. This is also an amide, and if you have two R groups attached like this, this is also an amide. The difference is these are all amides, but this first one is a primary amide, this one is a secondary amide, and this one is a tertiary amide. So since the nitrogen here that I'm highlighting in red, since it's attached to two carbons, this one is actually considered a tertiary amide. All right, let's take a look at the one that's in blue. There's a lot less functional groups in this one. There are actually only a couple of functional groups in here. Can anybody name a functional group in this molecule that I have highlighted or drawn in blue? What if I put a circle around this one right here?
That's the carboxylic acid.
It's not a carboxylic acid, right? Because a carboxylic acid, the oxygen has to have a hydrogen attached to it.
And it's a
Right,
carbon.
this one goes, we have a carbon doubly bound to oxygen, then we have an oxygen, then we have another R group, right? This is an R group over here. So this would be
An ether?
ester. No,
Ester.
it's an ester. Yeah, so this one is an ester. So we have, this is an ester, and so we'll put that here. This is an ester. What about this one here? This oxygen that's sandwiched between two R groups. I heard somebody say it a second ago.
An ether.
An ether, yeah. So this is an ether. Yep, that's fine. No problem. Then there's one more here, which might be a little tricky, but you see this nitrogen right here, it's attached to 1, 2, 3 carbons. So that makes it a tertiary amine. So if we circle all this, this is a tertiary amine. All right, I have another molecule drawn down here. We've seen all of these functional groups so far. Can anybody name them maybe a little quicker this time? Maybe not. That's okay.
Looks like there's an ester on one side.
Yeah, there's an ester right here. Absolutely. So this would be an ester, right? Because an ester is when we have a carbon doubly bound to oxygen, an oxygen, and then another R. I'll put an R prime, meaning that it can be different. So this, yeah, definitely. Any other ones in here? What about this one right here? I have an oxygen between two R groups, right? When I have oxygen between two R groups, that would be an ether here. And can anybody name this one here? If I circle all of that. Remember that when you have a carbon with a double bond to oxygen, then you have a nitrogen with a hydrogen and an R group. This is a secondary amide. So here we go. So this is an amide. All right, let me draw another molecule then and see if we can get a couple other ones in. So maybe some that we haven't seen this evening. So if I draw something that looks like this, I'll orient it a little bit easier for you guys. There we go. And then if I do something like that. And let me put this out here too. No, yeah. There's one here that might not be evident. I don't remember if I went over it with you in class, but there's two of them for sure that we went over in class, and I'll clear up the last one. Anything here that anybody recognizes?
Maybe an aldehyde?
Aldehyde, absolutely, yeah.
Aldehyde.
Yep, 100%. Yep, this is an aldehyde right here. Aldehyde, right? When you have an R group with a carbon with a double bond to oxygen, but instead of an R group or an oxygen, you have just a hydrogen. That's an aldehyde. Yes. Right. A carboxylic acid, you'd have to have an oxygen in there. So this is an aldehyde. Any other ones?
An alcohol.
Yeah. So what I wanted to say about this is you're 100% right. This is an alcohol, right? I cannot argue with what you said. However, when you have an alcohol attached to an aromatic ring, so this is aromatic, right? If you have an alcohol attached to it like this, this is called a phenol. Okay, so I'll just throw that out there. This is called a phenol. It's a type of alcohol, you know, and you know what? On your first exam, alcohol will probably suffice, but we'll put here that this is a phenol. It's a special type of alcohol. And if you're wondering, like, what the hell makes it special? Well, the reason why a phenol is special is because it's the hydrogen on the oxygen is a lot more acidic than the hydrogen on an oxygen of, say, ethanol or methanol or something like that. Okay, we got one more in here. This is one we haven't mentioned tonight. Can anybody identify this guy here? When you have carbon with a double bond, and you've got two R groups attached to it.
Is that a ketone?
Absolutely. Absolutely. It is a ketone. Perfect. Hey, you guys are killing it. All right. So hopefully you took the time to watch my video that I posted about functional groups. I know there was a couple of functional groups that aren't covered in our class, but they actually will come up later on in the class, just they didn't come up in chapter 1. Well, next what I thought we would do is take a look at a structural formula and see if we can condense it. So this is question 10.25a. I'm just going to write the structure down here. So I'm going to write a complete structural formula. I hate writing these down, but hey, we got to do what we got to do to learn how to condense structures. So let me just make sure I don't mess anything up here. Give me a second. And then over here. Okay. There's our molecule. So we have a total of 5 carbons in this molecule. I'm going to start on the left-hand side, and then I'm going to go towards the right. So you can see that right here, maybe I'll color code this. So here we have a CH3. So we're going to start with that. We're going to put CH3. And next to that, we have a CH2. Let's write that down. We have CH2. Next, it gets a little bit trickier, right? Because we have a CH, right? We have a CH, but we have 1, 2 CH3s attached directly to it. So the easy way to condense both of those would be to use an open bracket and then put CH3, close the bracket, and then put 2 like this. And that tells us that we have 2 CH3s attached to this CH. Give me a thumbs up if you follow me on that one. Okay. Is anyone there in the chat? I'm typing.
I'm on mobile, so I have no idea how to actually thumbs up here.
Yes,
Okay, okay.
I'm following too.
No, okay, great. Okay, great. Let me just double check here. Let me just double check. One student says they can't join, so I'm just going to check to make sure that the student is on the team. Yeah, the student is on the team. That's strange. Okay, where was I? All right, we're just going to have to keep moving. In the meantime, let's try another one. Let's try this one. And I don't want to try anything too big because they're so annoying to draw. But let's try, this is 10.26. And this is 10.26b. It's kind of a funny one. But hey, organic chemistry is so hilarious. So let's draw the whole thing. I'm really drawing as neatly as I can. And this one, I think I can actually ask you guys what your opinion would be if anybody has any thoughts about how we could condense this interesting structure here. Does anybody have an idea where we could go, what we could do with this guy?
Would it maybe be C and then parentheses CH sub 3 and then 4? I don't know if I got that right.
Yeah, you know what? I don't know who this is, but that's the best possible explanation you could have given.
Okay.
I couldn't think of a better way to explain it myself. All right, so what the student is saying is, she said, well, look, you got this carbon in the center, and then you have 4 groups attached to it, and all 4 of them are identical. Right? So then she said, well, why don't you just, do this, Mr. Dion? She said, put the carbon in the center. Maybe I'll color code it. We'll put the carbon in the center. And then she said, well, there's 4 CH3 groups surrounding it like that. So that would really be the easiest way to condense that one. Anyhow, it's kind of a funny one, but it's good. Let me just look here. And by the way, BTW, if there's any questions that anybody wants to look at, if you're thinking, oh, I already looked at this one, I didn't like it, or I couldn't figure it out, just holler it out. And Mr. Dion is always happy to look at any question from the book. I have a good question for you guys. And this is one where somebody is going to have to unmute their mic and speak up. This is question 10.35. It's just a conceptual question. So 10.35 says, why are hydrocarbons not water soluble? That's the question. And again, there is no trick. Mr. Dion does not like trick questions. Could anybody comment on this? And I'm not looking. Go ahead. Sorry.
Is it because they're non-polar?
Absolutely. Absolutely. Right. Could you explain to me why a hydrocarbon is non-polar?
It's, I would guess because there's hydrogens that kind of surround the majority of the hydrocarbon, and thus the bond between carbon and hydrogen is not a polar bond.
Okay, so you guys are you're going at it here. So Haley, we're not on any particular page. We're at question 10.53. We're just discussing a question from the back of the book, from the back of the chapter, from the end of chapter 10. Okay. Look, you guys are in an area, but you're not quite there. So let me make it even simpler for you. Somebody says covalent bonds. Somebody says something about hydrogens. Look, the bottom line is this. If we go back to these two compounds here, these are both hydrocarbons, right? These are both hydrocarbons. The bottom line is this. In a hydrocarbon, okay? In a hydrocarbon, there are only two types of bonds, carbon-hydrogen bonds and carbon-carbon bonds, okay? Both of which are non-polar. So just by definition, look, there's only carbon-hydrogen bonds and carbon-carbon bonds in a hydrocarbon. If there's no polar bonds in a hydrocarbon, it could never be polar. It doesn't matter the shape of it, the length of it, doesn't matter. If it's only made out of carbon and hydrogen, it's impossible for it to be polar because there's no polar bonds. Whereas water, my friends, water is polar, okay? And like dissolves like. So that means polar solvents are going to dissolve polar substances. Okay, so a non-polar hydrocarbon is not going to dissolve in polar water. Does that clear it up? Give me a thumbs up or a hey, hey. Like, yeah, that makes sense, Mr. Dion. Kind of crazy as I thought. All right.
Makes sense.
All right, I'll take it to the bank. That's good. That's good. Again, if you have any questions, this guy is always happy to discuss anything to do with organic chemistry. Well, I'm going to try a nomenclature question with you guys. And this is going to be based on, you know, me kind of testing you as to whether you actually watched the videos and, you know, tried some of the problems. So I'm going to try a question. Now let's pick something tougher than that. It says here, name each of the following using IUPAC. So let's hear 10.65. We'll just call it name the following. So this is something that I didn't lecture on during our live lecture, but I posted plenty of videos about nomenclature. So I'm going to start by drawing the first compound, and you can start sharpening your nomenclature skills while I write the molecule down. So this is A. And while you're thinking about that one, I'm going to go ahead and write B. Give you more time to think. All right. Yeah. What about A? Does anybody have any idea where we'd start to name A?
I'm just throwing this out there. I'm not sure if this is
Hey.
nomenclature, the IUPAC version, I mean, but is it hexane?
No, it's not hexane. So what we do when we name an organic molecule is we start by finding the longest continuous chain. Okay? So if I was to start over here and I said 1, 2, 3, 4, like that, is that the longest continuous chain? Keep in mind, we can't backtrack, okay? We can't go, 4, 5, 6. No, it doesn't work that way. So the longest continuous chain is found by trial and error. In this one, the longest continuous chain is this chain of carbons right here. It's got 5 carbons in it. So that tells you that the longest chain, if it's got 5 carbons, we call that the parent chain. And when we have 5 carbons in a row, this is some kind of pentane. Okay? The next thing that we do, now that we have identified the parent is a pentane, we number the carbons. 1, 2, 3, 4, 5. And we number them in such a way that we give the substituents, now here there's only one, we give the substituent the lowest possible number. Now, it doesn't matter if I number it going from left to right or if I had gone from right to left. In this particular case, there are many cases where it won't work this way. Oops, I didn't mean to do that. Anyhow, there we go. So could anybody tell me what kind of substituent this is? If I just have a CH3, my methane will become a So a CH3 group would be a methyl. So this would be 3-methylpentane. 3-methylpentane. Again, I would encourage you to always watch the videos before coming to class. Make sure you watch all of them. They're not even all that long, really, and they will cover all the content. Let's take a look at the next one. I find the longest carbon chain. Let's see, is it, oops, I need my highlighter. Is it 1, 2, 3? Heck no. Is it, 1, 2, 3, 4, 5, 6? Yes, it is. Now, somebody might be saying, Mr. Dion, what if you did this? 1, 2, 3, 4, 5, 6. What if you had done that? Well, the answer is it wouldn't matter how I traced the 6 carbons if I had gone like this. Either way, you're going to end up with the exact same answer. Let me show you. If we connect these carbons here, you can see that we have what? 1, 2, 3, 4, 5, 6 carbons in a row. So that's going to be our parent. So that means this is some kind of hexane, because hexane has 6 carbons. We've got 2 substituents. We've got a substituent at carbon 2, and we've got a substituent at carbon 5. These are both methyl groups, right? These are both methyls. So that means we have a 2,5-dimethyl. And so we put all that together, and we get 2,5-dimethylhexane, like that. Okay. Well, let's try one where we have to take a name and then draw the structure. Let's try 10.63. So this is 10, where's my pen? 10.63. Here we go. So let's try drawing some of these. First, why don't we try B? We're going to draw 2-iodo decane. And we're going to draw 2-iodo decane using a bond line structure. We're not going to use a condensed formula because it's too long to draw 10 carbons. So look, if my parent is a decane, decane has 10 carbons in a straight line. How would I draw a bond line structure that has 10 carbons? Look, I start with 1 when my pen touches the paper, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just this molecule is decane, but that's not what I want. I want 2-iodo decane. So I'm going to number the carbons. I'll start on the left. It wouldn't matter if I started on the right. I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And on the second carbon, I'm going to put an iodide, like this. And there you go. Now I've drawn 2-iodo decane. Just move this down and make it a little prettier. Oops, I don't know what I'm doing wrong here. Come on. Select tool. All right, good enough. All right, there we go. Let's try another one where we have to draw something. So this is 10.63. We'll do D. So this is 10.63 D. And we have to draw 1 bromo, 2 methyl pentane. Okay, so our parent is a pentane. Let's start by drawing that. 1, 2, 3, 4, 5. On carbon 1, so let's number them 1, 2, 3, 4, 5. On carbon 1, we have a bromo. Bromo is for a bromine, so we'll put a bromine on here. And on the second carbon, we have a methyl, and a methyl is a CH3, like that. I'll just leave it blank because when a bond ends like this in midair, we know that that is a CH3. And there we go. We have 1-bromo, 2-methyl pentane. Give me a thumbs up if this is helping you with your nomenclature skills a little bit. All right. Well, let's try some that are cycloalkanes. It's almost 6 o'clock. Let's see here. Let's do 10.8, 10.86. Let's try that one. So we're going to do 10.86. And we'll start with A. So it's this. Draw the best I can. There's a problem here. Ah, crap. There we go. There's one. I'll let you think about that one. And then we'll do C. Okay. Okay. Does anybody have a name for A?
The loop throws me for a loop.
Okay, so this is a cycloalkane, right? So we have a cycloalkane. We start with 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, right? So on and so forth. We have cyclopropane when we have 3 carbons. Up here we have cyclobutane, cyclopentane, right? Cyclohexane, cycloheptane. Okay, so this is some kind of cyclobutane, right? Because we have 4 carbons. We have a carbon here, a carbon here, a carbon here, and a carbon here, right? I could have drawn it like this: CH, CH2, CH2, there's another CH down here, right? You could draw the exact same thing like this, but you see how annoying that is to have to draw all of those carbons. A bond line structure is much more powerful. Okay, so now that we know that it's a cyclobutane, we're going to number the carbons in the cyclobutane, and we want to give our substituents, this time plural, we have 2 of them, we have 2 bromines, we want to give them the lowest possible numbers. So we'll start with the number 1 for one of them. So we have 1, 2, 3, 4. That means we have a 1, 3 dibromo cyclobutane. Now there's one other thing to consider. Can anybody tell me what it means when I draw the line as a shaded in what we call a wedge? These are wedges. Can anybody tell me what that means?
They don't lie on the same plane.
No, these two actually do lie in the same plane. Could you just tell me what the wedge means by itself? Right here we have a dash, right? There's a difference between a wedge and a dash. Could anybody tell me what the difference between a wedge and a dash is? So the wedge means the bond is
Towards us?
Yes, it's coming out of the page. Okay, and a dash means bond is going into page or screen or whatever. So since both of these bonds are coming out, they're on the same side of the molecule. So therefore, they would be cis. Right? When you have 2 bonds on the same side, they're called cis. Cis 1,3-dibromo cyclobutane. And when you have 2 bonds, as in the second example here, that are on opposite sides, can anybody tell me what the opposite of cis is?
Trans.
Right. Exactly. So this molecule would be trans 1,3-dimethyl cyclohexane. All right. Let's try another one. Yeah, let's try another one. What if I had this molecule? If I had something that looked like this. There. Could anybody name that molecule? This is 10.85B.
Is it 1,3-cyclopropane?
So here, you're right that it's a cyclopropane, right? We have 3 carbons. So this is some kind of cyclopropane, but we have 2 substituents.
Oh.
We have 2 chlorines, and we want to give them the lowest possible numbers. If we were to do this 1, 2, 3, that's not the lowest possible numbers. We'd have to go 1, 2, 3, right? Because a 2 is lower than a 3. So this would be cis, since both of these are on the same side, they're both wedges. So this would be cis, cis, 1, 3. Spacer, aren't I? This dichloro cyclopropane. Okay, remember in organic chemistry, numbers and letters are always separated by a hyphen or a dash. Numbers are always separated by a comma. All right, so that's a little more nomenclature practice there.
I have a question.
Yeah, shoot.
Can you explain why it's 1,3? Because
Oh, sorry, it's supposed to be 1, 2.
okay, then never mind.
I was testing you. Good. You nailed it. All right. Let's see. There's so many nomenclature problems in here. Does anybody have a problem that they want me to go over specifically? No? Okay, let's take a look at some reaction problems then. This is from the very last section of the chapter. There's a few reactions that you have to learn, and one of them is a combustion reaction. So let's try, this is 10.107. Okay, and the first question is this. We have 2. That makes it too easy. Jeepers. Let's try it like this. C3, C2, 2, 3 plus O2 gives you what? So who can tell me what happens, what kind of reaction we have when we take a hydrocarbon, right? Can anybody name this hydrocarbon right here? One that I have circled, 4 carbons straight in a row.
Butane.
Exactly, right. Methane, ethane, propane, butane, pentane, hexane, ethane, octane, nonane, decane. Right, so this is butane, and it's being combined with oxygen. What happens when you take butane in a lighter and you combine it with oxygen from the air in a spark? What do you get? What are the products you get from that?
Carbon dioxide.
That's one of them, yeah. What would the other product be?
Water.
Exactly. You end up with carbon dioxide and water. So could anybody tell me what kind of reaction this is? When you take a hydrocarbon, combine it with oxygen, and you produce CO2 and water.
It's a combustion reaction.
Exactly. This is combustion. Okay, so if we have a combustion reaction, let's balance it out. So if we look at the formula of butane, I'll just write it below. It's C4H10. So that means we've got a total of 4 carbons. If we've got 4 carbons for this molecule, but we've only got 1 in CO2, that tells me we need to put a 4 in front of the carbon dioxide. Next, we have 10 hydrogens over here, but we've only got 2 over here. So if I put a 5 in front of my water, 5 times 2 gives me 10. So now my carbons and my hydrogens are balanced. I have oxygen over here by itself. Let's tally up the total number of oxygens on this side. Can anybody tell me how many total oxygens there are on this side?
13.
Yeah, there's 13, exactly.
Yeah,
so there's 13 oxygens here. So what times 2 gives me 13? The answer is 13 over 2. So now my reaction is completely balanced. Everything is perfectly balanced, except one thing I learned in teaching in the States is that they don't like to leave fractions in their balanced equations. There's nothing wrong with the way it's written, but generally speaking, we like to eliminate the fraction. So we'll take this entire equation and we'll multiply the whole thing by 2 to eliminate any fraction. So when we do that, we end up with 2 butanes plus 13 oxygens gives us 8 carbon dioxide and 10 water, like that. And that's our perfectly balanced combustion reaction. All right, let me give you another question, another type of reaction that you have to learn in this chapter. If I take cyclohexane, this is cyclohexane right here, and I treat it with something, I get this plus hydrogen chloride. Can anybody tell me what this question mark is? What do I treat? What would I treat the cyclohexane with in order to get chlorocyclohexane and hydrogen chloride?
I mean, it has to have chlorine.
That's right. Absolutely. How many chlorines do we have over here? We have 1, 2. Right? So that means I would treat it with chlorine. This is a halogenation reaction, okay, which is a type of what's called a substitution reaction, because you're substituting one of the hydrogens on the cyclohexane for one of these chlorines here. And then the hydrogen will get combined with the other chlorine to make HCl. So make sure you go over halogenation reactions. I'm going to stop there.